Okay, so last night I asked you to try page 17. It was solving, they're not words, so we'll say cross number puzzle. And I want to talk about a couple of the problems that you would have seen here to talk about how you would have approached them, because that's going to play into what we're going to do for today as we're looking at solving our radical equations. So if we take a look at number 4, I've got the square root of x equals 15. How would you solve for x here? What would you do to get x by itself? I would square both sides, right? Because a square will undo that square root. We saw in our polynomials unit when we were solving, if I had something like x squared equals 9, we could undo the square with a square root, and we did the same thing to both sides. This is using that same idea, but sort of in the opposite direction. So we're going to square both sides. So I would get whatever 15 squared is, leave that as 225. So that's what you would have filled in here, 225. Number 4, I have the square root of not just x this time, but x minus 10. What would I do here? So you're looking at, I know what number would give me 5 if I took the square root of it. Yeah. What if I didn't know what number gave me 5? What if I had 57 here? How could you work through that? What'd you do up here? Squared it to get rid of the square root, right? So since you already know what number had to have given you the square root of 5, you're working from there. But if I didn't know this, I could approach it the same way. I want to get rid of the square root, so square both sides. I get x minus 10 equals 25. Then I want x by itself, so move the 10 to the other side. And we get 35. Same process, but one more step once I take that square, once I get rid of the square root. How about number 9? I've got 3 times the square root of something equals 6. I want to get x by itself. What would be my first step to get x by itself? Divide by 3, right? I want to get the square root by itself, so divide by 3. I would get the square root of x equals 2. And then just like we did above, I want to get rid of the square root, so square both sides. And you would get x to be 4. This is an idea that we're going to use today. Maybe not exactly this. Not every problem that we look at will be a square root. We'll see some square roots, but that won't be everything. But this idea of get the root by itself and then undo that root is what we're going to see for today. So on the next page, on page 18, okay, we've got a couple sort of similar introduction problems. So I want you to take a minute and give each of these a try. So I just picked 3 problems from page 17 that were very similar to these. Give these a try. What am I going to do for the first one? I want x by itself. Other way around. Not square root, but square. That's the one that we want. Right? I already have the square root. I want to undo it. So we square. Right? I know those, we're going to mix up those terms inevitably because they're so close. But yeah, we're squaring here. So I get x equals 64. How about the second one? What do I do? I heard somebody say it. I square it. Yeah. I want to get rid of that square root. So we get x minus 2 equals 9. and then add 2 to both sides to get x by itself. How about for our last problem here with my first step? Yeah, I want to get the root by itself to start. So we divide both sides by 4. So I get the square root of x equals 5. And then square both sides, just like we did for that first one. We would get x to be 25. Okay, so again, these ideas we're going to use today as we're looking at solving these radical equations. Okay, so again, I want you to notice the first thing you did was get the root by itself, and then we squared something. Okay, I had to get the root by itself and then I squared. So let's take a look at a couple more problems like this. This time instead of square roots, we've got cube roots. So for our first example, A here, I want to get the root by itself. That means this 4, this time that minus 4 is not under the root. Okay, here that minus 2 was under the root. Okay, it's kind of trapped under there. Here it's not under the root, so it needs to go. Okay, my first step is to move this. So I get the cube root of x equals 4. And now this is a cube root. How do I undo a cube root? I cube it. Yeah, to undo a square root, we squared. To undo a cube root, we cube. So this would be x equals 4 cubed, which is 64. Now, one thing that we'll need to do with our solutions for our radical functions is check them, okay? We can have what are called extraneous solutions with our rational exponents and our radical equations. An extraneous solution means a solution that we find mathematically. I didn't make any mistakes in my work when I was solving, but if I were to check that solution on a graph, which we'll talk about in a little bit, or if I were to plug it back into the equation, that value plugged in for x doesn't actually work. Okay, that's called an extraneous solution. So we have to check these for extraneous solutions. Okay, so to check, I'm going to take that value and plug it back in. So the cube root of 64 minus 4, I'm going to know, does that equal 0? The cube root of 64 is 4. Does 4 minus 4 equal 0? Yes, so this one's okay. Now let's try B. So cube root again. This guy is pretty similar to our 4 root x that we had up at the top. My first step here is going to be to get rid of this 2 in front. I've got 2 times the cube root of x. I want just that root by itself. So I'm going to divide by 2. And then I've got the cube root of x plus 1 equals 4. Now that I have just the root on this side, okay, now this is a problem like the second one up top. So in order to get at anything under the root, I have to get rid of the root. Since it's a cube root, to get rid of it, I'm going to take this to the 3rd power. I'm going to cube it. So I would get x plus 1 equals 64. And then to get x by itself, subtract 1 from both sides. So we get x equals 63. And then again, check your solution. So we have 2 times the cube root of 63 plus 1 equals 8. 63 plus 1 is 64. The cube root of 64 is 4. So we have 2 times 4 on the left. Is that equal to 8? Yeah. So this solution works. Now, I want you to remember that we can represent roots as powers, right? Instead of using a root, I could have used an exponent instead. So I could have also said that this would be x to the 1/3 power minus 4 equals 0. These are equivalent. X to the 1/3 and the cube root of x, that means the same thing. Okay, we can convert between those forms. So if I have this rational exponent instead of that root version, I can still solve this equation. Okay, you could, if you wanted to, rewrite it as a root and then do what we did here. So if you started with this, you could say x to the 1/3, that means the cube root of x, and then work from here. That's fine. You could also keep it in that exponent form, and I'm going to show you what that looks like. So this is the same problem, right? X to the 1/3 power minus 4. I'm going to start off exactly the same way by getting the thing with the exponent by itself. If you remember when we solved using square roots in our polynomials unit, when I had something like 2x squared equals 8, our goal was to get the x squared term by itself and then take a square root, right? Then get the thing with the exponent by itself, okay? Or if I had something in a quantity squared, we had to get the thing with the exponent by itself. Same idea here. So I'm going to start by moving this 4 to the other side. So I get x to the 1/3 power equals 4. And now what I want is x to the first, right? Just plain old x. What I have is x to the 1/3. To get rid of this 1/3, to reduce out that 1/3, I can use one of my exponent properties, okay? I can take this to a power, and I'm going to choose a power so that this reduces to 1. So my question for you is 1/3 times what would give me 1? Yes, 1/3 times 3 would give me 1, right? This would be 3/3, which is just 1. What I'm using here is the reciprocal power, right? The exponent I have is 1/3, so I'm going to take it to the 3/1 power. Okay, use reciprocal power. So I'm going to raise this to the 3rd power. And whatever I do to this side, I have to do to this side as well. When I have power to a power here, I've got 1/3 times 3/1. That's 3/3, which is just 1. And then that equals 4 to the 3rd power. Well, 4 to the 3rd power is 64. I got the same answer that I got from number 1 part A because this is the same problem. I represented that root differently in number 2, but it's the same problem. Okay.
Can you just change that problem to that problem and it'd be the same?
Yeah, that's what I talked about at the beginning. So if you had something like this and you were like, this is a cube root, I would rather work with the root, you can absolutely do that and then work through it this way. Some of us, I think, would probably prefer to keep it in that root format, and that's absolutely fine. I also would bet that some people in here would rather be able to use those exponent rules, especially when we get to stuff that's going to have like a goofy root and then also an exponent. Keeping it in an exponent form might be something that other people prefer. So if you wanted to, you could also take this and rewrite it in this form to solve it. Okay, both of them work. They mean the same thing. You're going to get the same answer. And then if I had this format, I would still check this answer. The difference is that when I check it, instead of having it written as a root, it would be 64 to the 1/3 power. Oops, minus 4 equals 0. 64 to the 1/3 power, that's still the same thing as the cube root of 4, right? So this is still, or the cube root of 64, which is 4. So that's still 4 minus 4, which is still 0. Okay? Same problem that we worked through 2 different ways. Now let's take a look at another example. Notice this is not the same as the B that we did above. So this is its own thing, okay? This is a new problem. The first thing I want to do is get the thing with the exponent by itself. So if the 2 and the x were in parentheses with that exponent outside, I would already have the thing with the exponent by itself. But I don't see any parentheses here, okay? This is a mistake that I see fairly commonly. There's no parentheses here, which means only x has that power. So I have to get rid of the 2. So we have x to the 3/2 power equals 125. And now, if you're a root person, you like the roots better, you could, if you wanted to, rewrite this as the square root of x to the 3rd power equals 125 and go from there. So you'd have to get rid of the cube and then get rid of the square. Or if you wanted, you could put the cube underneath. So you get rid of the square root and then get rid of the cube. That's fine. You can solve from this. The other thing that we can do, this is going to take 2 steps. The other thing that we can do is use that exponent, right? That reciprocal exponent like we did here, and do it in 1 step. Okay. So I want to multiply 3/2 by something so that I get 1. That's going to be, again, the reciprocal. This would give me 6/6, which is just 1. So I'm going to raise both sides to that reciprocal power. I have 3/2 right now. I'm going to take it to the 2/3 power. So my exponent here is just 1. Power to a power, I multiply. When I multiply these, I get 6/6, which is just 1. And then I need to simplify this guy. So for this, I am going to rewrite it in that root form. I talked about this the other day, but for me personally, it makes more, it like clicks, it makes more sense if I can see it in that root form. So that's what I'm going to do. So this would be the cube root of 125, and then I'll square that. The cube root of 125 is 5, and then 5 squared is 25. So I would get x to be 25 here. And then again, I'm going to check this. So this would be 2 times 25 to the 3/2 power. I want to know if that equals 2/15. So this would be the square root of 25 cubed. The square root of 25 is 5. 5 cubed is 125. 2 times 125 is 250. So we're good there. No extraneous solutions. Questions for me so far? Okay, turn the page. And notice we've got a mix of stuff with fractional exponents and roots. As we work through these problems, I'm going to keep them in whatever format they are currently in. Okay. When you're working through them on your own, on your test at the end of the unit, if you want to switch stuff to roots, you can switch stuff to roots. If you want to rewrite stuff as exponents, that's fine too. Just to give us practice with both. If it's in an exponent form, I'm going to keep it that way. If it's in a root form, I'm going to keep it that way. Okay, that way we get practice with both. For C, I've got an exponent form. Okay, so I want to get the thing with the exponent by itself. That means this 2 needs to move to the other side. So I get 4x minus 7 all to the 1/2 power equals 3. And now I want to get rid of this exponent. So to do that, I'm going to raise this side to the reciprocal power. So I'm going to take it to the 2/1 power. I'm going to square it is another way to think of that. Now, for this problem, I want you to notice, if I were to have rewritten this as the square root of 4x minus 7, I would get rid of the square root by squaring, right? So I'm still doing the same work. I'm just representing this part a little differently. And so if I square this side, I have to square this side as well. Power to a power means I multiply. 1/2 times 2 is just 1. So I have 4x minus 7 all to the first power, which is just 4x minus 7. Okay, once the exponent's reduced to 1, I don't need to write it in parentheses with that exponent anymore. So 4x minus 7 equals 9. And now I've got something linear, right? This you could have done in 8th grade, this part right here. So I'm going to move this 7 to the other side. I get 4x equals 16. Divide both sides by 4. So I get x to be 4. And then don't forget to check your work. I'm going to check my solution off to the side here. So this would be 4 times 4 minus 7 to the 1/2 power plus 2 equals 5. Oops, 5. 4 times 4 is 16. 16 minus 7 is 9. 9 to the 1/2 power is the same thing as the square root of 9, which would be 3. 3 plus 2 is equal to 5. So I have a solution there. X equals 4 is a valid solution. Now, D is a little different. I've got multiple roots here. Since I've got 2 different terms that have a square root, right? I've got 2 separate roots. I want to separate them. That's a little different than the stuff that we've done before. When we were working with polynomials, if I had an x squared term and another x squared term, I wanted them on the same side and we combined them. Here, we're going to separate them, okay? So I'm going to move this 2 root x to the other side. So I have the square root of 3x minus 2 equals 2 root x. And now that I've got this root by itself, and this root as by itself as it can get, I'm going to square both sides. Now be careful on the right-hand side. It's not just the square root of x that I'm squaring. I also have to square this 2. On the left, square and square root cancel each other out, and I get 3x minus 2 equals. Over here, I would get 2 squared, right? This goes here. And then when I square the square root of x, that's just x. So I have 3x minus 2 equals 4x. Now I want to move the x's to the same side. So I'm going to move the 3x over to the 4x. And I get negative 2 equals x. And again, don't forget to check your solution. So this would be, and remember I'm plugging it into the original, not after I've moved anything. This would be 3 times negative 2 minus 2 minus 2 times the square root of negative 2 equals 0. Under our first root, 3 times negative 2 is negative 6. Negative 6 minus 2 is negative 8. So I have the square root of negative 8 minus 2. And then since I have a negative here, I'm going to pull out an I. So I've got the square root of negative 8 minus 2i root 2. Since this is negative, I also have an I that I can pull out. And then 8 I could simplify. I get a pair of 2's and an I to pull out, so that would be 2i root 2 minus 2i root 2. 2i root 2 minus 2i root 2, is that going to be 0? A thing minus itself. 4 minus 4 is 0. Yeah. Is root 2 minus root 2 0? So how about 2i root 2 minus 2i root 2? Yeah. Imaginary numbers here, which I know sometimes makes us a little uncomfortable, but as long as this side equals this side, we're good. And that is a valid solution. Questions for me so far? Okay, let's take a look at our next example. So for E, I've got my root by itself over here. So to undo that root, I want to square both sides. And be careful on this one. We're not squaring the individual pieces, we're squaring the whole side. And when I have something in parentheses, x minus 4, right, squared, doesn't mean x squared minus 4 squared. It means x minus 4 times x minus 4. So we've got to distribute here. So this would be x squared minus 4x minus 4x plus 16 equals 2x. So I've got x squared minus 8x plus 16 equals 2x. Since I've got a quadratic now, I'm going to move everything to the same side and solve by factoring. If you wanted to complete the square on this, you could. If you wanted to use quadratic formula, you could. I know that this factors once everything's on the same side, so I'm going to factor. So I would have x squared minus 10x plus 16 equals 0. Factors of 16 that add to negative 10, that would be negative 8 and negative 2. So I have x minus 8 times x minus 2. So for my solutions, I get x to be 8 and 2. Now I need to check both of these. So I'm going to check x equals 8. So that would be 8 minus 4 equals the square root of 2 times 8. 8 minus 4 is 4. And then 2 times 8 is 16. So 4 is the square root of 16. Yep, that one works. And now I'm going to check x equals 2. So this would be 2 minus 4, need the parentheses there, equals the square root of 2 times 2. 2 minus 4 is negative 2. And this would be the square root of 4. Now, I want you to remember that when we use square roots to help us solve in our polynomials unit, when we introduced the square root to the problem ourselves, we had to account for both options, the positive and the negative. But we didn't introduce the square root to this problem. So this is actually an extraneous solution, okay? And I'm going to show you the graph here. I'm going to pull up my calculator so we can take a look at the graph of this one. So we can sort of reinforce why this one's extraneous. All right, here's my calculator. And you can check all of the equations that we're solving with the graph. I want to show you checking them on one where we've got an extraneous solution so we can see why there's not a solution there. So what I'm going to do is type in x minus 4. That's the left side of my equation. I'm going to hit enter. Then I'm going to hit the tab key. And I'm going to type in the right side of my equation, which was the square root of 2x, and graph both of those. So the two solutions that we saw were 8 and 2. So I would expect intersections when x is 8 and when x is 2. Okay, so I see one intersection. Let's find where that is. Menu, analyze graph, intersection. Click on either side. And I have an intersection where the x value is 8. That's the solution that we checked and said that was good. What about when x is 2? Do I have an intersection here? Do these graphs touch when x is 2? No, right? And this is a square root graph, so it only goes in this direction. This is a line, right? So it goes straight, right? It's got its slope that it continues on. I don't have an intersection point there. All of your equations you can check with your graph. If you get something that looks like it's going to be extraneous, like what I saw on part E, problem E, it's a good idea to double check with your graph, especially then to make sure that I didn't make a whoops with my arithmetic, okay? But that's why that other solution is extraneous, right? It's not on the graph. And since we didn't introduce that square root, it would only be a positive result that I would expect. Questions for me on E? Okay, let's take a look at F. F is kind of similar to D. I've got more than one cube root this time. For D, we said get those roots on opposite sides. We already have that here. So I'm just going to cube both sides to get rid of those roots. So this is x plus 4 equals 2x minus 5. And we're down to something linear here. So I'm going to move my x's to the same side. I get 4 equals x minus 5. And then get x by itself by moving that 5 to the other side. And I get x equals 9. Again, I want to check my solution. You can check this on the graph if you want. Graph this side, graph the other side. I'm going to check it algebraically by plugging in 9 for x. So I'd have the cube root of 9 plus 4 equals the cube root of 2 times 9 minus 5. Over here on the left, I have the cube root of 13. And then on the right, that's equal to the cube root of 2 times 9 is 18. 18 minus 5 is 13. Do we know the cube root of 13? 13 is prime, right? It's not going to have a nice cube root. Does it matter that I don't know the cube root of 13? No. The important thing is I have the same thing here as I have here. So even though I don't know what this simplifies to, it's the same. So we're good. I would like you now to try G and H. Try G and H. Okay, let's take a look at these. For G, we're in exponent form, so I'm going to keep it in exponent form. The whole left-hand side is to the 3/2 power. So I'm going to take the whole left-hand side to the reciprocal power, to the 2/3 power. And then I'll do the same thing on the right. When I multiply these exponents, I would get 6 over 6, which is just 1. So I only have 2x plus 7 on the left. And then on the right, I want to simplify this. I'm going to rewrite it in that root form. So this would be the cube root of 27 that I square, which would be 3 squared, and that's 9. So I get 2x plus 7 equals 9. Move the 7, I get 2x equals 2. Divide by 2, I get x equals 1. And then don't forget to check. So this would be 2 times 1 plus 7 to the 3/2 power equals 27. 2 times 1 is 2. 2 plus 7 is 9. So this would be the square root of 9 cubed. The square root of 9 is 3. 3 cubed is 27. So that solution works. For H, I've got a root over here and it's by itself. So I can go ahead and square that side, and that means I'll square the other side as well. Okay, this is going to be really similar to E. So I get x minus 2 on the left, and then I'm going to have to distribute on the right, since I have x minus 2 times x minus 2. So when I distribute, I get x squared minus 2x minus 2x plus 4. And then since I have x squared and x terms, I'm going to move everything to the same side and do my combining all at once. So I have 0 equals x squared. This would be minus 5x plus 6. Again, this will factor. If you wanted to complete the square here, you could. If you wanted to use quadratic formula here, you could. Any of our appropriate quadratic solving methods would be fine. I'm going to choose factoring. This would give me x minus 2 times x minus 3. So my solutions would be x equals 2 and x equals 3. And then I need to check both of them. So when I check x equals 2, I have the square root of 2 minus 2 equals 2 minus 2. So this would be the square root of 0 equals 0. That is true. This one works. And then I'm going to check x equals 3. So this would be the square root of 3 minus 2 equals 3 minus 2. 3 minus 2 is 1. So I have the square root of 1 equals 1. That is also true. I want to take a look at the solutions on the graph for H. Okay, we had 2 actual solutions on this one. The last time we had 2 solutions, we got one that was extraneous. So I want to show you what it looks like when we have 2 solutions on a graph and nothing extraneous. I'm going to pull my calculator back up here. And let me get rid of this. And graph H. So for H, we had the square root of x minus 2. And then the other side was just x minus 2. And it's tight, but I can see 2 places of intersection there. If I wanted, I could zoom in here. So I could see that a little better, a little easier to see there. And then I could find each of those to check using the graph. So analyze, find the intersection. Remember, we can only find one at a time. So I have an intersection when x equals 2, which was one of our solutions. And then find that other intersection. And it's when x equals 3. So 2 solutions on the graph there. Questions for me for today? Okay. Next time we're going to continue working on solving these radical functions or functions that have a rational exponent.